Okay, we're going to go ahead and look at exponential functions a little bit, followed by logarithmic functions. So over here on the graph, our red is an exponential function. And then we're going to look at in the inverse of that. And for any inverse function, you can reflect that red over the diagonal y is equal to x line, and you would get its inverse, is what we have there in blue, which is a log function. Any log function is always the inverse, a function that undoes your exponential function. Now, why might we need to learn about logs? Well, if you're dealing with sound and you look at the intensity of sound, sound is typically measured in decibels. However, it's a logarithmic scale. So a sound that's a decimal that's, say, a 7 and you go to 8, that's really going up by 1, but it's 10 times louder when we're dealing with decimals. Also, if you're looking at the Richter scale for earthquakes, it's also a logarithmic scale. If you're looking at the acidity, or how basic something is in chemistry, or how acidic something is in chemistry, that's also a logarithmic scale. So there is a lot of application to different situations dealing with logarithms. Now, take a look at these here. Look at this to see what are you doing to get this, or look at this, how is that related to this here, or how is this last one related to this one over here. So I've color-coded things here to help you see. We would read this problem here on the left as log base 3 of 9 is equal to 2. That's how we would read that. So your base is a little subscript here, is when you rewrite it over here, you really take your base, swing it over, and it hits the 2 up as your exponent. So you get a 3, hits that 2 up as the exponent, and then it gives you what's after your 9. And so that's really what we're doing. What we have here on the left is referred to as the logarithmic form, and what we have here on the right is your exponential form. And that's what we have really on this next screen. Here is your form for your exponential, and here is what we call your logarithmic form. A logarithmic form has a log in there with a subscript after it, which is your base, which is the blue. And just remember, a logarithm is really representing an exponent. And so a log is representing an exponent. And you'll notice that that green, which is equal to the log, is really becoming your exponent over here. And you might be wondering, well, why do we need to learn about logarithms? Well, if we take a look at this one here, we can easily get a 4 on each side. Remember, 16 is a 4 squared. That's really a 1 over a 4 squared, so it's really a negative 2. And then, since you have the same base on each side, you can set the exponents equal and solve it. But when you look at the one over here on the left, there's no way to rewrite 5 or rewrite 7 so you can get the same base on each side. So that's why we need to go ahead and use logarithms. Logarithms allow us to solve it for that exponent without the whole idea of just using guess and check. Now, one other thing important to remember dealing with logarithms, that b has to be positive. And we also know that x has to be positive. So basically, whatever's after your log has to be positive. So now we're going to use this whole definition of a logarithm, going log form to exponential form, to help us rewrite this problem here from the exponential form, because it's something to a power, to the logarithmic form. Now I have the color-coded version here, so what we have right here is very similar to this right here. So we're going to have to go log of our base. Our base is the thing that the exponent is on. That goes as a subscript after your log. What is your exponent up here? The 3 is what goes on the other side all by itself. What was on this one side all by itself is what goes after your log. So we'd say log base 4 of 64 is equal to 3. That's just basically using that definition of a logarithm going from the exponential form to log form that you see there at the bottom. We also have the reverse process. Here we have the log form, and so we need to take it from this form here and rewrite it in this form here. Color coding it, it would be like this. So we'll put down our equal sign. Our blue 16, I'll put here. Our 2 becomes the exponent, and our 256 goes over here. By the way, if you did go ahead and take 16 squared, it does give you 256. Now, another way you may want to think about this is you basically take your 16, swing it over, hits the 2 up as the exponent, and that's what we have right here, equals that 256. So now we need to evaluate these. We're trying to figure out what does this equal. So we would say it's our base, which is 6, to some unknown power that we're trying to figure out, ends up being our 36. So you got to think, okay, 6 to what power is 36? So that means our unknown power that we're looking for is 2, because a 6 squared is 36. We can use that same approach over here. We have our base of 3. It would be 3 to our unknown power that we're looking for is really equal to that 1 over 81. Now, remember, 81, you guys know, is 9 times 9, but that's a 3 and a 3, followed by another 3 and a 3. So this is a 1 over a 3 to the 4th would be equal to our 3 to some unknown power. So our 3 to some unknown power, because I'm going to take this and bring it up, it would become a negative exponent. Now that I have the same base on each side, that means our exponents are equal, so that whole green exponent just simplifies down to just negative 4. So this log base 3 of 1 over 81 is just another name for negative 4.